Principal component analysis afforded us two things: dimensionality reduction, reducing the complexity of the original representation of the data, and that representation afforded something else, which was a richer representation that allowed for things like face recognition. Now, PCA is not without its limitations. Let me remind you what we did. We have some initial representation X, and we are going to represent it. We are going to change the bases from the canonical bases, pixels in the case of images, to a new basis, P sub I. If these X's are originally in an n-dimensional space, let's say we have 256 by 256 images, a 256 squared dimensional space, the goal here is to have a new basis of only size m, where m is much, much smaller than n, affording, again, both computational efficiency, but also a richer representation to allow us to do things like recognition. Now, there is a big, big, fat, whopping assumption that went into PCA. And I said it several times, but I may not have made it explicit, so let's make it explicit. We are doing a linear transformation. In fact, an orthonormal transformation. The basis that PCA projects onto is simply finding axes within this space to project onto. And what's very nice about that is that it can be a very efficient and very effective tool, but it is limiting. It is, after all, a linear transformation. Think, for example, the difference between logistic regression and LDA, linear discriminant analysis, and linear SVMs versus nonlinear SVMs and neural networks. Nonlinearities bring power to our computation. Linear are nice because they're closed-formed and analytic and easy to compute, but they, like PCA, have fundamental limitations. So here's an example of a limitation. Let's say my data in this two-dimensional world look like this instead of those nice elongated data with a clearly defined principal axes. So I've got a cluster over here, I've got a cluster over here on the side, and then what appears to be two clusters on top. So if I ran PCA on this data and I wanted to project from a two-dimensional space into a one-dimensional space, what would I do? Well, I take all these data, pack them into a matrix, zero mean, compute the covariance matrix, compute the eigenvectors of that covariance matrix, and grab the largest eigenvalue eigenvector, which in this case will be this horizontal axis because that is the axis of maximal variance of the data. And I'm going to throw away the other axes, and what's going to happen is that. Is that good? Well, some of it is good. I preserved the variance between this cluster and between those two clusters in here, but I lost a lot of discriminability here because the variance along this dimension was much smaller than here, and so we lost one of our clusters, if you will, and that doesn't seem great, but I can't do any better with PCA. I'm sort of stuck because it's a linear transformation. Now, there are many, many, many different variants of PCA. There is kernel PCA and nonlinear PCA that try to respect the structure of this. There is so-called manifold learning, lots of really interesting techniques for doing dimensionality reduction while preserving some of the structure in the original space that goes beyond linear transformations. We are going to talk about one of those called tSNE, T-distributed stochastic neighbor embedding. Terrible name, but very cool idea. And here's the intuition here. In this space, we have global structures, the relationship between these points and these points, and we also have local structure, the fact that these are clustered together and these are clustered together. And what we'd like to do is respect both. We'd like to keep things that are distant apart from each other, but we'd like to keep this stuff here sort of respecting the local structure. So here, for example, is a different 2D to 1D transformation. I've got lots of room on this axis, so maybe what I should do is make some room for both of those clusters, and now in this embedding, you can see I've got the best of all worlds. I've reduced from 2-dimension to 1-dimension, I get dimensionality reduction, and I'm preserving the local and the global structure that underlies the original data, and that's what tSNE is going to do. I don't think it's going to surprise you that this is going to be a non linear optimization because we're doing a nonlinear mapping. I'm not going to go through the full-blown optimization and all the details of tSNE. tSNE is now built into most libraries. I'm going to show you an implementation of it, but I do want to give you some intuition as to how the technique works. Let's start with some data in a three-dimensional space. And here I've just got these two clusters of 4 points right here. What we're going to do is take a single data point, p sub I, and for a little neighborhood around it, I don't need to look at the whole space, but just a little sphere around here, I'm going to compute the following distribution, which is take this point x sub I, and on the numerator of this value, p sub ij, I'm going to compute what is this, by the way? This is just a normal distribution. So this is e to the minus the vector norm between point I and point j in red and blue divided by some sigma. This tells me essentially how similar are these 2 points relative to the similarity to all the other points. So notice here, this is a sum over all k of the difference between the ith point and the kth point within some sphere around the ith point. So that is, how close are these 2 points relative to what's happening in some area around me? What does this capture? This is a distribution of how similar I am, how the local structure and the distribution of the data in the original, in this case, 3-dimensional or high-dimensional space. Now, I want to project that data, say, into a 2-dimensional space. And each point here is going to be represented in a 2-dimensional space. This is my dimensionality reduction. And what I'd like to do is preserve that relationship in the original space in terms of distances. So I'm going to compute a similar metric in the low-dimensional space. Let's call that qi. So here I've now got qij is the relationship in the embedding space between the ith point and the jth point. Now I'm going to call these y because I've projected them down. This is the new representation. And the denominator here is, again, just the relative, the sum of all the points within a small neighborhood. So how similar is this relative to everything else? And now what I want to do is what? Well, I want to reduce dimensionality. We know this. But the other thing I want to do is preserve local structure and, of course, global structure as well. And so what we're going to do is we are going to find the embedding through a nonlinear optimization that maximizes the Kullback-Leibler distance between these 2 distributions, the distributions of Pij for all ij rather, and Qij for all ij. So this is the standard distance metric between 2 distributions. One in the original dimensional space, that's P, one in the reduced dimensional space, that is Q. Obviously, this is a nonlinear optimization. I've got this messy Kullback-Leibler distance where I've got the log or the ratio of these differences, and I've got these things embedded in the normals. This is not a closed-form solution, but what tSNE has done very well is find a mapping that can maximize this and create an embedding in a low-dimensional space that respects more of the structure than can be accomplished with a simple linear transformation like PCA. Now, something that's very important to distinguish between PCA and tSNE is that PCA is representational. What do I mean by that? I mean that my vectors, I've created a basis, and my vectors are represented with respect to that basis. tSNE doesn't compute a basis. It's simply computing a mapping from a high-dimensional space to a low-dimensional space. And the reason why it's not computing a basis is once we start talking about linear basis, we're sort of restricted to linear transformations. And so what it's learning is a mapping, and tSNE is really about visualizing high-dimensional data in low-dimensional space. PCA is also about visualizing high-dimensional data in low-dimensional space, but it's also representational, which means that the representation in the low-dimensional space can be used for things like face recognition or object recognition. Okay, now what we're going to do is, just by way of intuition, this is what tSNE is for reducing dimensionality and respecting local structure and going beyond linear transformations. And when we come back, we'll just go ahead and do the implementation, and I'll show you an application of that for character recognition.